have set a lot of background which we will need, for example, a lot of discussion, and today's discussion also on photon emission. You need later in terms of looking at the electronic structure. So we are near the end of looking at physical structure of the surface and bulk in some way, and we're at the final, hopefully the last two lectures on determining the structure of the surface, and then we will move on from there to look at the electronic structure of the surface and then of material and nano objects and things like this. Okay. So today I'd like to sort of finish off what we started last near the end, which is to look at the sort of limitation of the electron diffraction technique, so-called low energy electron diffractions. Just to point out some of the limitation, it's not a almighty tool. It is something very useful, but it's not. It does, as with most technique, it has its own limitations. So we had this last time. We talked about why is LEAD a service-sensitive technique. The reason really is just because the energy that for LEAD is usually in the range of below 500 electron volt. It means that it can sample inelastic mean free path within your solid is roughly 2 to 3 monolayer. So you cannot, if you look at the universal mean free path that we have looked at before, it is inherently sensitive just because the kinetic energy is low. So, and the second part is that we are talking about in electron diffraction, we are talking about elastic scattering of the electron beam, low energy electron beam, and if you look at so-called elastic cross sections, scattering cross section. Cross section is a fancy word for probability in physics. So it is just think of cross section as probability of being scattered. And so when people talk about large cross section, it means high probability of scattering. So in this case, if you're talking about elastic cross section, it's usually of the order of 10,000 megabarn. This is particle physics terminology when they are talking about scattering elementary particle in the high energy physics facility. So this megabarn unit directly taken from high energy physics, and really it just means 10,000 megabarn. You can think of it as 1 angstrom square. Really, I mean it's kind of like how much area that you have in order to scatter your beam. So if the larger the area, the larger the cross section. You know, you're boxing. So you can think of, let me just draw something. So you think of a cross section like this, right? You're bashing the electron into this, right? So the bigger you have this cross sections, the more chance that this electron beam gets scattered away. So that's why the word cross section. And this area dimension is quite relevant because if you have bigger area, like 1 angstrom square, then it will be better than 0.01 angstrom square, this sort of thing. Okay. So it's a measure of probability of getting scattered. So 1 megabarn, the jargon is 1 megabarn is 10 to the minus 18 centimeters square. So in the old days, of course, the particle physicists use CGS unit, so-called CGS unit, not SI unit. So the unit of length is centimeters, not meters. So that's the history of this in IGMAR. The point is that in elastic scattering is 10,000 megabarn or 1 angstrom square. So that's elastic scattering, and if you're looking at inelastic scattering, it's a lot less. So here you're really primarily talking about elastic scattering. Elastic scattering. inelastic electron scattering, meaning that the electrons suffer a energy loss, losing energy, is much less. This probability is much less. It's about 1 to 100 megawatt. So it's about 1% to 1%. So it's really quite small. So most of the electron is as elastic scatter. If you send it this thing, most of the electron, 99% of the electron will keep its existing energy. It's elastic scattering, and the rest, like 1% or less than 1%, will suffer some energy loss. Okay, so that's the physics that you throw the electron at material like this. What happened then is that most of these, so when you're talking about this elastic scattering, you need to measure how the electron beam gets scattered off. So you need to measure the angular distribution, so to speak. So here's a general way of describing angular distribution. So you make a polar plot. So you have intensity from 0 to here. So this is an intensity scale, and then you go around as a function of angle, and this length from the origin represent the intensity that you will see. So to represent the cross sections. So you go from forward scattering. So this is a measure of forward scattering in this direction. Forward scattering, you have of course the most probability, right? As you go away from the forward direction, then the probability drop. And then there's a minimum. It's an interesting minimum. I won't go into the physics of it. There's a so-called Ramsau minimum in here. Every cross section will have this minimum. And then you have a secondary loop, and then you have backscattering cross sections. Okay, so this is forward scattering, and this is backscattering. And the point is this: the point is that if you this is low energy electron beam, so the scattering distribution is broadened in the angular direction. If you increase the kinetic energy of the electron, you have the forward scattering, as you would expect, will be more focused in the forward direction. So this lobe here will be narrowed down. Right? This lobe, with the width of this angular distribution, is wider here, whereas in high energy electron it will be more forward. Okay? This is known as the searchlight effect, because you can essentially point in the right direction, and target which atom you want to scatter. Okay? And what we are measuring really is not the forward direction really, it's actually the backward scattering. We are measuring at this tiny lobe. So you're looking at the sort of forward direction here. This is narrow, all the lobe will also be narrow. The width of the lobe will be narrow. So yeah, we're very finely focused effect. So in here, for example, if you're talking about low energy electron lobe, the backward scattering cross-section is actually quite comparable to the forward scattering cross-section. And that is in fact what we measure in LEAD, which is the backward direction. It is also elastic scatter. It just bounces back at the gun, that you have. So here's our picture. The electron beam comes in, forward scattering is go into your solid. The one that come up that give you diffraction pattern is actually this loop here that gives you this. Okay, so that's how physicists think about these electron scattering cross section. You can calculate all these things. They are immense theory, physics theory, because you are just talking about electron scattering, but the electron scattering is a difficult problem in physics because of the Coulomb potential. The 1/r potential is difficult to treat in here. So the typical way to think about these scattering theory is that people like to think about in terms of incoming wave. So incoming wave of this electron beam coming in this way, in green coming this way. You write in terms of a plane wave, e to the I k dot r kind of thing, and this is the outgoing wave, e to the I k prime dot r. Right? So this is the either the ingoing forward scatter or backward scatter.